So here we're going to talk about Fourier's law and thermal conductivity. Fourier's law is the relationship that tells us how the heat flux relates to the temperature gradient. The thermal conductivity is the proportionality constant between the heat flux and the temperature gradient. So to begin, we maybe, sort of historically, might think about who Jean-Baptiste Joseph Fourier is. Well, he was perhaps one of the greatest mathematicians that has ever lived. On top of that, he was probably the first heat transfer scientist and heat transfer researcher. You've heard of his name with relationship to things like Fourier series, Fourier decomposition, things like that. And he really came up with these tools to better understand heat transfer processes. All right, so as we said, there's a relationship that exists between the heat transfer rate power per unit area, and so we call that a flux. So this is the heat flux, and I should have put a double prime over here. So Fourier's law tells us the heat flux is proportional to the temperature gradient. If you think about what the temperature gradient is, the temperature gradient has units of, say, kelvins per meter. So it's a temperature difference over some length. And I guess it's not surprising. We would expect that as the temperature difference goes up, the heat transfer rate also goes up. We would expect as the thickness of a material increases, that the heat transfer rate decreases. So Fourier noted these types of issues through some simple measurements and deduced the form of this law. That proportionality constant here is called the thermal conductivity, and so we'll talk a little bit more about what the thermal conductivity is and its properties. One of the things that I want you to notice is that in terms of the proportionality, it also has a negative sign. That negative sign is important because, let me sort of put it over here. It says that if the temperature gradient is positive, so positive temperature gradient, I'm going to make this x, and this is the temperature as a function of x, T of x. This is a positive gradient because the slope is increasing. So a positive slope is a positive gradient. And what that implies, if you think about it, before we even talk about sort of say the temperature here is 100 degrees Celsius and the temperature here measured is 20 degrees Celsius. If I were to ask you which direction the heat is flowing, you would clearly tell me that the heat is flowing in the negative direction. So when we have a positive value for the gradient, or that slope, we have a negative direction for the heat transfer rate. So that please remember that the requirement for that negative sign. All right, so this gradient that we talked about is a vector math notation. And what it says sort of simply is that it's got three components. It's dt dx, dt dy, dt dz if we're working in Cartesian coordinates. If we just focus on one particular direction, in the x direction, qx could look like minus k dt dx. And there's a special case of that. It's called for an isotropic material. We'll talk about that in a second. An isotropic material is one in which the thermal conductivity does not have a directional dependence. So in some sense, these are the simplest ways that this can be described. So this simplest cases are for these isotropic materials. There are more complicated materials that might be worth just understanding. Depending on the coordinate system, so if we're in cylindrical and spherical coordinates, this heat flux in the radial direction could look like minus k dt dr. As again, we've said the proportionality constant is the thermal conductivity. In general, this thing is something called a second order tensor. We'll talk about what that means in a little bit more detail. All right, so a tensor, you can think about a tensor as, so sort of simplest, it looks like a matrix, but it's not a matrix. It's something that transforms from one sort of direction or one quantity to another quantity or direction. So it's a mathematical relationship or mathematical object with transformation properties. And transformation, you might just think about as mapping. So one of the things that this matrix or this transform does is it takes elements of this gradient, dt dx, dt dy, dt dz, and it maps or reflects them into the components of Q. And these three components of Q are Q in the x, y, and z directions. So practically speaking, if we had, say, some object, some complicated object or simple object that we're trying to understand how heat flows within this object. So we're interested in the heat flux vector within this material. At some location here, we can imagine that there exists an infinitesimally small cube, and that infinitesimally small cube has some properties associated with it. If we blow that cube up, we look at this cube, and again, it's really a point, but mathematically, it's sort of simpler to think about it as a cube. You can imagine that there are x faces, y faces, and z faces on this cube. And so on a z face, for example, you could say, well, even in the z face, I've got a z direction on the z face. So I've got a z direction, I've got an x direction on the z face, and I've got a y direction on the z face. Well, these properties of K are identifying both the face and the direction that this K changes. So it says that at some location, if I look at a particular face and I ask the question about what happens in a particular direction, it's basically saying that K can vary depending on this choice of face or direction. And so face, again, is sort of a normal. I'm looking in a particular direction, and again, for this sort of volume, and I'm looking at a particular face in a particular direction. What's sort of interesting about that, then, is that this mapping says that for an anisotropic, a non-isotropic material, one that has directional dependence, that the heat transfer rate in the x direction is dependent on gradients in the y and z direction. It's non-physical, but mathematically it's consistent, and there are materials that follow that type of behavior. They're unusual. More typical are materials like wood, which is a laminate, which is called orthotropic. So if you imagine looking at a piece of plywood edge on, so that's a very bad drawing of a piece of plywood. So let's clean that up just a little bit here. So again, for this piece of plywood, you can imagine that the grains run along it as such. So there is a laminate or grain structure that runs in this piece of wood. What that means is that the heat transfer rate in this direction, you might call that, say, the z direction, might be very different from what it is in the y direction. So for a piece of wood, we might expect that there's a different, depending on where we sit and how we're looking relative to the grain, that the orientation matters and the thermal conductivity changes appropriately. In this class, we're really just going to focus, because we're really trying to just understand basic issues in heat transfer physics, we're just going to focus on so-called isotropic materials. That is, materials that in any direction that I look, the material property is the same. So this says that the thermal conductivity looks like a scalar, behaves like a scalar, and in such a way that, again, in any particular direction, it really has the same value, although it might be a function, for example, of the temperature. So being a function of the temperature doesn't say anything about the directional properties. It simply says that at different points, it has different values. That's a very different issue from saying at the same point, depending on which direction I look, it has a different value. Okay, so make sure that that's clear. Okay, well, now that we've sort of thought about what this thermal conductivity is, it's a proportionality between the temperature gradient and the heat flux rate, the heat flux vector. It's important to understand values of the thermal conductivity. So as thermal engineers, properties like the thermal conductivity of air are useful. And so the thermal conductivity of air is approximately 0.02 watt per meter Kelvin. Thermal conductivity of water, another very important fluid, is more like 1, but we say it's 0.6 watt per meter Kelvin. And these are room temperature values. These do change with temperature, but it's important just to understand what happens at these sort of basic conditions. As we look at different phases of materials and different types of materials, we see a vast range of thermal conductivities. So we're going all the way from 10 to the minus 2 watt per meter Kelvin to 10 to the 3 watt per meter Kelvin. So a factor of 10 to the 5 in terms of the overall range here. Not surprisingly, gases have the lowest thermal conductivity. The smaller the molecule, the faster the molecules sort of bounce around and the higher the thermal conductivity. So hydrogen has a relatively high thermal conductivity. We said that air was over here at about 0.02. As we look at liquids, we get increasing thermal conductivities. Insulating liquids like oils are the smaller values. So for example, 0.2 as an example of an oil thermal conductivity. Whereas as we look at a liquid metal, like liquid mercury, we get significantly higher thermal conductivities. Insulating solids can be anything from a foam. So in a foam, we oftentimes have air gaps or some sort of other gas filling the foam. And so it's a composite of sorts with relatively low thermal conductivities. In fact, the thermal conductivity might intersect with those for gases. And even for non-insulating solids that we're not intending just to use for insulation, there's a range of thermal conductivities. Depending on the type of plastic, the density of the plastic, the molecular weight of the plastic, we have relatively low thermal conductivities to oxides, which may have significantly higher thermal conductivities. The very highest thermal conductivities are for pure metals, and that's distinctive from alloys. And alloys are different from pure metals because of the grain structure. So the grain structure in a metal is almost, it's a little bit, it's not quite the same as this laminate. It's a place where the vibrations that are causing the transfer of energy can bounce off of. You can think about it in a simple way. Or you can think about it in a different way, that if it's particle-based, that there are imperfections and impurities that the notional particles that are responsible for transfer, whether it's an electron or some other particle, that those are places that they actually bounce off also. So this description of particles and waves as far as the ability to transfer energy is very clear in electromagnetic systems. And so in electromagnetics, so when we talk about radiation, this will become clearer. But in electromagnetic systems, for a long time in physics, there's been an understanding that there's sort of a dual property of both waves and particles. So there are different descriptions that are useful in different contexts. Well, interestingly enough, this will also play out in conduction systems. Before talking about that, it's important just to think about the simplest system, which is a fluid system, and specifically a gas system. And so in those systems, there's a long history in theoretical physics that's called kinetic theory of gases that has said that there is a description that allows us to think about gases as comprised of these particles. So you might think about cold gases, or a cold side of this gas mixture, and a hot side. The hot side is this red side. And understanding that these particles move randomly and eventually collide off others of their type or whatever else exists in there and scatter. But these are all energy transfer processes that are occurring. And these are, again, random transfer processes. So based upon that, it says that if there's a plane in this system, one can understand the transfer processes that are going. So for the kinetic theory for gases, it's pretty clear that the fluid density is going to play a role. There's going to be a speed over which these gases move, this thermal speed. This thermal speed, the square of the thermal speed looks like the temperature, so that's sort of a thermodynamic relationship that holds. There's going to be a spacing that matters. It's this interparticle spacing is the distance that these guys will travel before they collide with something and move in a different direction. And again, this is for this dilute gas system. For metals, similar description applies where we think about electrons as the transfer mechanism. So it's either valence electrons or free electrons. The correspondence between the fluid density is going to be the free electron density. Correspondence to the thermal speed is going to be some sort of electron drift speed. And the interparticle spacing is going to be some sort of, it's a similar issue, it's a lattice dimension. The one that's sort of different is, again, if you think about a ceramic material, for example, you say, well, gee, there are no electrons really that are free or available there. And what happens in this system is quite distinct, is that there are waves that can be set up, crystalline waves that are set up in these materials, but sort of invoking this idea of this duality. In electromagnetic systems, the particles are discussed as photons. In these systems, the notional particle is called a phonon. And so it's a notional particle that represents this transfer process in these systems. And so the microscale carrier is called a phonon. There are different types of phonons. The speed of sound, because this is really sound wave in some sense, is the associated carrier speed. And similar analogies exist between that and other issues in kinetic theory. So to sort of close, the molecular basis for thermal conductivity. Thermal conductivity can be thought of as this proportionality constant in terms of the temperature gradient, but it's more fundamental that there's a molecular description for this thermal conductivity. That molecular description of thermal conductivity says that it's dependent on some molecular speed, the number of molecules per unit volume, a length scale over which these carriers collide with each other and with other things, the molecular mass of the system, a specific heat, and this Boltzmann constant, which is this relationship between energy and temperature.